Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello students, this is Teacher Pasco, and allow me to welcome you again to the TV learning programs. Today I will be with Senior 4 students, chemistry students, with an assessment, or the end of unit assessment for unit number 6, trends in the chemical properties of group 1 elements and their compounds. So we discussed a lot. We worked out so many exercises. And today we are going to have an assessment to test our level of understanding, if we have understood what you have been studying in this unit number 6. So we are going to start with the correction of the last homework I gave you. And here we have the first question. Explain the following observations. Lithium iodide is more soluble in hexane than in water. We know the answer to this question, and we know substances which are soluble in organic solvents. Hexane is an organic solvent, but water is inorganic. So if lithium is more soluble in an organic solvent, then it means that even though it is formed by a metal and a non-metal, suggesting that it will be ionic, but the fact that it is soluble in hexane than in water shows that lithium iodide is more covalent than ionic. So why is it more covalent than ionic? It's because of the high polarizing power of lithium and the high polarizability of the iodide ion. And then when we combine both, we find that the lithium iodide is a covalent substance. We know the polarizing power and polarizability. So lithium has a very small size, high charge density, making it having high polarizing power, and the iodide ion, with its very large size, it can be easily polarized, making the compound more covalent than ionic, and hence soluble or more soluble in hexane than in water. Lithium carbonate is less stable compared to sodium carbonate. The thermostability, here it is stability in terms of heat, thermostability increases when substances are becoming more ionic. And here also it is because of the high polarizing power of lithium due to its small size and high charge density, making lithium carbonate less ionic and then with weaker electrostatic forces compared to sodium carbonate, in which sodium cation has a large size and small or low polarizing power, making sodium carbonate more ionic with stronger electrostatic forces than lithium carbonate, and then that makes this compound more stable on heat. Explain how you can distinguish a solution of sodium chloride and that of cesium chloride. Very simple. We can use a flame test. We can use a flame test. You remember for sodium we have a yellow flame, and for cesium I think it's violet. So if you use a flame test, you can distinguish the two substances. Which one between lithium hydroxide and potassium hydroxide is a stronger base? The basicity depends on how many, or the relative concentration of OH ions in the solution. And the relative concentration of the OH ions will also depend on the solubility of these two substances. We know that solubility increases as you move down the group, making potassium hydroxide more soluble than lithium hydroxide. And if you consider same concentrations, then potassium hydroxide will produce more OH because of being more soluble, making it a stronger base than lithium hydroxide. And last, write balanced equations for the thermodecomposition of lithium nitrate and potassium nitrate. Lithium nitrate decomposes like this. Lithium nitrate we know that when it is heated, we produce lithium oxide plus nitrogen dioxide plus oxygen gas. Okay? 4, 4, 2, and 1. And for potassium nitrate, it looks like this. When you heat it, you produce potassium nitrite, which is solid, plus oxygen gas. 2 and 2. So why do we have different products? We have different products. Why? Because of what we have seen as the abnormal behavior of lithium. Lithium, which behaves more than group 2 compounds, group 2 elements like magnesium. Why? Because of its very small size and high polarizing power. So lithium nitrate decomposes differently from other group 1 nitrates, giving us these two different equations. And that is because of the small size of lithium and its high polarizing power, which makes it behave differently. Okay. Now we go to the exercises. Complete the equations below. We have a number of equations. We remember how the group 1 oxides react with water. Here we have potassium hydroxide in aqueous solution with copper sulfate. We know how the hydroxides of these elements precipitate metal cations from their solutions. We have also the sodium peroxide reacting with water. Remember these equations. An acidic oxide with a hydroxide, acidic oxide with an oxide, basic oxide, lithium reacting with an acid. So let us complete the equations. Complete equations. This is what you have to always remember about the group 1 chemistry. We have sodium oxide reacting with H2O liquid, and what do we produce? We produce sodium hydroxide in aqueous solution, of course, and here if we balance, we get 2, okay? And we've seen that, remember, we've seen that we cannot predict the solubility of these oxides, the oxides of group 1. Why? Because they react with water to give us basic solutions, okay? So we cannot predict their solubility, as they cannot give you a solution. Instead, they react with the solvent to give you a new substance. Number 2, equation number 2, we have potassium hydroxide dissolved in water plus copper sulfate also dissolved in water. We have 2 solutions. And here it reminds us the precipitation reaction. We said that these hydroxides, group 1 hydroxides, they are able to precipitate metal cations from their solutions, their aqueous solutions, and they precipitate them as hydroxides. So we produce copper 2 hydroxide, which is solid, plus potassium sulfate. Remember, all group 1 sulfates are soluble in water. And here we balance, we get 2. Equation number 3. Equation number 3, it's sodium peroxide reacting with water. What do we produce when sodium peroxide reacts with water in the liquid form? We produce, when the normal oxide reacts, we produce sodium hydroxide. And what do we produce when it reacts with the peroxide? We produce the hydroxide still, but with hydrogen peroxide. Hydrogen peroxide, let's say it is dissolved in water, and then we use 2 here. 2 here is our equation balanced. We also use 2. Now we have 2 sodium, oxygen atoms we have 4, here we have 2 and 2, and the hydrogen atoms we have 2 and 2, so the equation is balanced. And if we go to the next equation, we have sulfur dioxide, that is equation number 4, sulfur dioxide, remember, non-metal oxides are acidic oxides, and when you react sodium hydroxide with a non-metal oxide, what do we produce? We produce sodium sulfite in aqueous solution plus H2O. So it is also a neutralization reaction because we produce a salt and water while we had an acidic oxide and a base, a basic solution. So here we have 2, and if you check, you will find it balanced. We have 3 oxygen atoms. Here we have 3. Sorry, here we have 2 and 2. That makes it 4, 3, 4. Hydrogen atoms, we have 2. Here we have 2. Sodium, we have 2 and 2. And on equation number 5, we have another acidic oxide. It's this one, carbon dioxide, which is a gas, plus potassium oxide. You remember the conditions for this reaction. The reaction takes place at a very high temperature. So we have carbon dioxide, gas, plus potassium oxide, and we heat the mixture at a very high temperature, and we produce potassium carbonate. Potassium carbonate, which will be solid, and we go to the last equation. The last equation is lithium solid reacting with a dilute acid. You remember what products are formed when these metals react with aqueous or dilute acids? Yeah, I hope you do remember. So we produce a salt and hydrogen gas. So lithium reacting with an aqueous acid, a dilute acid. Remember, the reaction, because of these metals being, group 1 metals being very reactive, you have to use a very dilute acid, and if you use concentrated acid, the reaction may be explosive and very violent. So you make sure that you don't use concentrated acids to avoid accidents. So we produce lithium sulfate dissolved in water, because even this acid is dissolved in water, and we produce hydrogen gas. So how do we call this reaction? It is a single displacement reaction. It's called a single replacement reaction. And here is it balanced. We need 2 moles of lithium. And the equation is balanced. Okay? Yeah. So let me give you like 30 seconds, and then you complete taking, or you finish taking the notes. You copy the equations, the balanced equations, in your workbooks. Okay? In your workbooks, you copy these equations. Okay? So hurry up, because we have more exercises to try. Here we have had the simple questions of just completing the equations, but remember, the chemistry of Senior 4 mainly focuses on explaining, okay? So you should always be able to explain what we observed, the observations we make. So here we have questions on another slide. How does each of the following properties, remember the variation of the physical properties, in this group. The following properties of the elements in group 1 change with the increasing atomic number. And then you explain. Property number 1 is the atomic radius. As we move down in the group, the atomic number increases. Okay? Now, how does the atomic radius change? The atomic radius, first property. The atomic radius increases as we move down the group. And why does it increase? It's because we are having an extra shell added. And the extra shell added makes screening effect increases or makes it increase more than nuclear charge. And the effective nuclear charge reduces, making the atomic radius to increase as we move down the group and as the atomic number increases. Number 2, we have ionization energy. With the increasing atomic number, it means that we are moving down the group. And moving down the group, the ionization energy, we know that it decreases. Why does it decrease? It decreases because, think about it, it's because the atomic radius is increasing. So if the atomic radius is increasing, it shows that the electrons are experiencing a weaker nuclear attraction. And if they are experiencing a weaker nuclear attraction because of a stronger screening effect, then it will require a small amount of energy to remove the electrons. And that is the reason why the ionization energy goes on decreasing as you move down the group. So moving down the group, ionization energy decreases, and that is because the atomic radius increases, making the electrons experience a weaker attraction, and then it requires a small amount of energy to remove an electron. That's very clear. Reducing property, or the reducing properties. Do you remember the metallic character and non-metallic character? We have seen that metallic character increases as you move down the group. And metallic character means or shows how easy an atom can lose an electron. The reducing property of a substance shows how readily the substance can lose electron. If we take the example, for example, let's say sodium. Sodium, when it reacts with chlorine, let's say I have chlorine, then sodium, they form sodium chloride. And what is the charge for this sodium? It's 1 positive, and that of chlorine, it's 1 negative. The oxidation number here has increased, so the sodium has been oxidized, but for chlorine, the oxidation number has decreased. So it has been reduced. But why has it been reduced? It has been reduced because sodium has given an electron to chlorine. Now, if we consider another example of lithium and the same chlorine, which one do you think will give its electron to chlorine more easily? Is sodium going to give the electron to chlorine more easily than lithium or less easily compared to lithium? We can use the ionization energy, we can use the metallic character. As you move down the group, the ability of losing electrons increases. So the reducing power increases. Okay? So sodium, which can lose an electron more easily, is the one which has a greater reducing capacity. It can reduce chlorine more than or more readily than lithium. So as we move down the group, ionization energy decreases. As ionization energy decreases, then it becomes easier to lose the electron, and the reducing property increases, becomes stronger. So the elements become stronger reducing agents. Okay? Reducing ability increases as you move down the group because it is easier to lose the electron. Now, how does the reactivity with water change? Reactivity with water increases as you move down the group. You remember the video I used to explain or to show how the reactivity changes. And this is because the ionization energy is also changing, is also decreasing. If it requires a small amount of energy to lose the electron, and these elements react by losing electrons, then even their reactivity will go increasing as you move down the group. The reaction becomes more and more violent as you move down the group. Electronegativity decreases as we move down the group. These are metals, and their tendency of attracting bonding pairs will go decreasing as you move down the group because the size is increasing. When the size increases, it shows that it becomes difficult for the nucleus to attract the electrons. So if the nucleus is not able to attract very strongly its own electrons, it won't even be able to attract extra electrons, the bonding pairs. So electronegativity decreases as we move down the group. On the next slide, here we are asked to explain how successive ionization energies of sodium will vary. Sodium, like other elements in group number 1, that is, let's say sodium, we have lithium, we have potassium, they are in group number 1. And in group number 1, we know that the electronic configuration will always end with 1 electron, okay? So for lithium, we have 2 and 1. Sodium, we have 2, 8 and 1. Potassium is 2, 8, 8 and 1. So the ionization energies, successive ionization energies, will increase as you move from 1 electron to the next electron, as you keep on removing electrons. The ionization energies increase. Why is it like that? First, it's because the remaining electrons are experiencing a stronger attraction. You are reducing the number of electrons, but the number of protons in the nucleus is constant. So the electrons will remain, so we experience a stronger attraction. But when you move to the second shell, to the inner shell, there is a big increase of the ionization energy because electrons are strongly attracted. You are removing an electron from an inner shell, which is closer to the nucleus, where the screening effect is low, and where the shell is close to the nucleus, and the shell is complete. Okay? Now, why is sodium ion formed in a normal chemical reaction than sodium 2+? This is because of having a single electron on the last shell. Number 4, explain how ionization energies of group 1 elements are related to their reactivity. We know this, as ionization energies reduce moving down the group, the reactivity increases, as it requires a small amount of energy to lose electrons. Which one between sodium carbonate and cesium carbonate will decompose at a lower temperature? Thermodecomposition. Which one between the two is more ionic? The one which has a cation with the larger size, and that is cesium carbonate. When we have a larger size, we have small or low polarizing power, and the compound becomes more ionic. With stronger electrostatic forces, then it will resist from being easily decomposed. Number 6, which one between lithium bromide and potassium bromide would be more soluble in water? Explain your answer. You remember the question we started with, lithium iodide. So between this one, which one will be more soluble? Lithium bromide or potassium bromide? It's potassium bromide, yeah. Why? Because lithium bromide, with its high polarizing power, with the high polarizing power of lithium, then lithium bromide will be more covalent. Being more covalent, it will be less soluble in water. So potassium bromide with the low polarizing power of potassium will be more soluble in water because it is more ionic. Okay? Good. I hope that is very clear. And here we have your homework. Complete these equations and include state symbols. I didn't put the state symbols here, and you will try to put them there. You complete the equation, you make sure it is balanced, and you include the state symbols. Lithium plus nitrogen. You remember one of the special behaviors of lithium. It reacts with nitrogen to produce the substances we call nitrates. So you will complete this equation, and don't forget to balance and write the state symbols. B, sodium hydride. The hydride ion here, in this compound, hydrogen has one negative. And then sodium hydride reacting with water. What do we produce? Make sure the equation is balanced, and you write the state symbols. And number 3, C, potassium hydroxide reacting with iron 3 sulfate. State symbols should be given, and make sure the equation is balanced. Explain the following and support your explanations with equations where possible. 1, variation of first ionization energy in group number 1. So here you will explain how the ionization energy, first ionization energy specifically, it varies from the top of group to the bottom of the group. And number 2, you will explain how reactivity of group 1 elements varies from the top to the bottom. You can use the example of the reaction with water. C, explain how solubility of group 1 chlorides, that means lithium chloride, sodium chloride, potassium chloride, how this solubility changes as you move down the group. And D, thermostability of group 1 nitrates. Group 1 nitrates behave differently when heated. So you will explain how the thermostability of these substances change. And you explain the abnormal behavior of lithium and its compounds. You will, of course, give some examples, and that's the reason why I said you will support your explanations with the equations where possible. So thank you very much for your attention. Thank you very much for your active participation, always being there to follow the program. See you next time. Keep in touch. Thank you.